Welcome to our next video. We're going to continue talking about framing the discipline of statistics and just talk a little bit more about some common statistical terms and some big ideas. So I'm going to jump back into the notes here, and I'm going to start here with the nature of a statistical claim. So we've talked a little bit about the nature of the statistical question, different types of statistical questions. So now I just want to talk a little bit about the types of claims that are appropriate to make from statistical results. And one thing I like to bring up is that a lot of folks talk about statistical results in terms of proving things, like this drug has been proven to be effective, or this drug has been proven to not be effective, and different things like that. And I would say that kind of language should be used very cautiously. It's more of a layperson language than I think really a scientist language, or at least it shouldn't be the language that that experts are using around statistics. And I think it really comes from a basic misunderstanding of what statistics is and the limitations around what we do. So the first thing that I would bring up here is that statistical claims are probabilistic claims rather than claims of absolute certainty. That we'll talk about when we get to things like p-values and confidence intervals, is that we're making claims within a level of confidence, right? So like we're 95% confident that this could be true, or that this is not true, or oftentimes even more confident, but it's still a probability at the end of the day, right? So the odds that, or the probability that you win the lottery is extremely low, but it's not impossible, right? So like I can show you the probability of you winning the lottery and say it's about 5 million to 1, but that doesn't mean that I have just proved that you can never win the lottery. I have just showed that it's highly, highly unlikely that you're going to win the lottery on that lottery ticket. So I always kind of like to caution people away from using those terms. It's not proving in the same way that something like mathematics is. Mathematics is kind of like an assumptional framework where we assume certain things are true, and if these things are true, then we can make claims of absolute certainty in that system under that assumptions. Real-world claims using things like statistics are of a completely different nature than mathematical proving. And then beyond just the probabilistic point, I would even just mention the limitations of the types of research that we do and the claims that we make with statistics. So I'll mention two here. When we talk about the next chapter, these are going to be kind of lumped under external validity and internal validity, which we will define and talk about a lot more in the next chapter. But external validity has to do with limitations in how broadly we can generalize this claim, right? So if I have good external validity, then it means that my claims generalize well to a larger population in a larger setting in a larger time. If I have poor external validity, it means that there's question marks about exactly who these results apply to and exactly what settings and times they apply to. So pretty much any time I do a study, especially when humans are involved, there's going to be some external validity threats. There's going to be things that limit how well I can generalize these claims that I have to keep in mind. Internal validity has to do with basically within the study itself, within this sample of people in this experimental setting, I am confident that this thing caused this thing to happen, or right, that this phenomenon is true. And even that, we can have a lot of validity issues. It has to do with the design of our study, whether or not there's other what we call confounding influences, things that could also explain what we observe besides what we think it is, or other just biases and errors kind of in the process. So there's a lot of things that can go wrong, and in pretty much any research study, there are limitations, there are validity threats. So when we make these claims from statistical results, I would never use the term prove. I might say that we're very confident in things, especially if it's a very well-conducted study, like if it's a randomized control trial with a lot of oversight and a lot of mechanisms built in to ensure appropriate protocols have been followed, then yes, we can make claims with a high level of confidence, but I would never use the term prove. All right, so just a few terms that we should also be familiar with, things that you've probably heard before, but we'll define them formally here. A data set versus a variable. So a data set is usually going to refer to like the spreadsheet. It's going to be all of the collected data and all of the variables that are included. So for example, if I did a survey, each question that I ask might be thought of as one variable, right? I have one question and all the different responses or data, types of data that were collected under that one response. But I'm going to have usually multiple variables in a data set, usually. So that whole set of data, like all the questions, all the measures that I collected, I might think of as on a spreadsheet, and I would call that my data set. Typically, when we create a data set, we usually label each column as a variable, like as a question or measure that we've taken, and each row is considered one observation. Oftentimes, one observation means one person. Sometimes if I'm collecting data from the same person multiple different times, then each time point is a row, right? So I might have person 1 time A, person 1 time B, person 1 time C. Those might be separate rows. So just keep that in mind that it's often going to be like one person, one unit, or one time point of data collected. Secondly, we have population versus sample. So a population is going to refer to the entire group that I have an interest in describing. So if I'm doing inferential statistics, oftentimes I'm trying to describe or make claims about a population by using data from this sample that I have from that population. So an example of a population that we might be interested in is the UIUC student body. And a sample I might be interested in is, 100 students from the UIUC student body. And I'm hoping that maybe their data and their responses can tell me something about the greater population, assuming the way that I sampled them to be kind of representative of the population across some key target demographics. And then lastly, on this list, we have parameter versus statistic. So a parameter is going to be a descriptor of a population. It's going to be some characteristic of a population. A statistic is going to be a characteristic or measure of a sample. So statistics are things that I can know, right? So I can know what these things are. However, parameters, I am probably not going to know what they are. I'm going to say I won't know what they are. I suppose it's possible I could know what a parameter is for a particular population in certain circumstances, but for the most part, I won't know what these are. And the idea behind inferential statistics in particular is I collect a sample, and I hope it's a good estimate of this parameter. I know there's probably going to be a little bit of error, but hopefully it's reasonably close to that parameter. So statistics are things that we can know. They're descriptors of our sample. Parameters are things that I probably will never know, and they're going to be descriptors of an entire population that I might be interested in. And also, N is just a shorthand for noting the size of the sample in the study that I'm looking at. So, for example, up here when I said I might sample 100 students from the student body, so N equals 100 in that case. And then just a brief thing down here is that oftentimes we think about the larger the sample, the better, and that is certainly true most of the time. However, don't discount small samples as, not telling us anything. So as we'll talk about, we can make claims with a certain level of confidence, even if I only have like 20, 25, 30 people in my sample, that I can still make claims with a level of confidence about what could be true. So don't discount small samples. We don't need a large percentage of the population in our sample. We don't even really need like a measurable percentage. The only thing that matters is that we're either collecting a random sample or doing something to ensure a representative sample. And it doesn't matter how large the population is, as long as we have some people who are representative of that population, then we can make claims with a level of confidence about what could be true about that population. All right, so we're going to do a couple practice questions here just to review some of the ideas we talked about. So here we have a description of a poll conducted by Gallup. So they conducted a poll to gauge the opinions of adult U.S. residents about gun laws. They contacted a representative sample of 1,526 people. So representative, as we'll talk about in a later chapter, just means they have done things to ensure that this sample of people looks like the population of U.S. residents, of U.S. adult residents. They probably did things like look at race, look at education level, look at gender, look at income, and just make sure that who is in their sample looks like who is in the U.S. population and kind of represents it appropriately. Among several questions asked on this poll, one asked about whether or not that person supported a complete ban on individual gun ownership, and 29% said yes. Okay, so who is our population here? So our population is going to be adult U.S. residents. That seems to be the population they're trying to describe here. Our sample is going to be the 1,526 people who responded, which means that N in this case is going to be 1526. Our variable of interest is, we could frame this or write this a couple ways, but I'll just say support of a complete ban on individual gun ownership. Oops, I'm going to write what I say. So support and right there might be other questions in this survey, so they probably collected some data and they have a data set with multiple questions in it. But this is the one question that's being described here, right? The one variable that's being highlighted here is whether or not they support a complete ban on individual gun ownership. The sample statistic we gathered here is the 29% who said yes. So 29% said yes, they do. And do we know what the population parameter is? Well, I would say no. But we hope that 29%, or at least Gallup hopes that 29% is a reasonable estimate. The true parameter could be a little bit different, and as we'll talk about in later chapters, there's ways that we can kind of estimate how much error we might expect given the sample size here. So given that they have 1,500 people, that can help us determine how far off we would expect the sample statistic to be. So it's probably not exactly 29%, but it's probably reasonably close. Like as we'll talk about with margin of errors, the margin of error is probably going to be around 2 or 3%, meaning that we're pretty confident that the true percentage is around 31, between like 27 and 31, assuming that they have a good sample, right? That they have a representative sample, that there's no biases in the question format or different things like that. Okay, identify each of these questions as probabilistic, descriptive, or inferential. So I collected basic health statistics on 200 people. What is the average height of my sample? So this is asking about my sample, and I'm describing my sample, which means that this is a descriptive statistics question. I collected some data. I'm reporting information about my data. The next question here is that 85% of the world population has brown eyes. If I were to find 200 people of diverse backgrounds, how many of them would I expect to have brown eyes? So here we're starting from some known information. We might call this the truth, as we talked about. This is, known supposedly information about this population, and I'm asking what could happen if I take a sample and I know this to be true. What would I expect to happen? So that makes this a probabilistic question. And I can calculate the probability of getting, 100 out of 200 people with brown eyes given this information, or 170, or whatever number I'm interested in. I sampled 200 people from a particular subpopulation, and 145 of them have brown eyes. Is there evidence that this subpopulation is genetically different than the population at large? So we're basically saying we have some subpopulation. We don't exactly know the proportion of brown eyes in this subpopulation, but we do know that we got data from 200 people, and 145 of them had brown eyes. So what could reasonably be true about this population? Like, what could that parameter be for this subpopulation? So this is definitely an inferential question. So right here, we have our sample. And then we have an open question about what could be true. What could be the truth, we might say. So this subpopulation is genetically different. So I'm going to say what could be the truth. All right, and then the last practice question on this page. You are reading an article online that asks, do people who tend to be out in the sun more report higher happiness levels? The article concludes that the researchers found a link between how much time people spend in the sun and how happy they are. Based on this language, are the researchers answering a univariate question, associative question, or a causal question? This one's a little bit tricky. So there's one that we can narrow or eliminate right away. It's not a univariate question because we're looking at the relationship between two different variables. The first one is how much time people spend in the sun. The second one is how happy they are, right? So we're basically asking, do these two variables have some kind of relationship? Now, is it associative or causal? And that really depends on this word right here. And I like to do this example here because link is a very tricky word, and I'm here to tell you that this is an associative word, but it's not necessarily a causal word. And you're going to see this a lot in literature when researchers are making associative claims, but the word might be a little bit ambiguous, but I'm here to tell you that if you see the word link, you shouldn't assume they're making a causal claim. They're probably just making an associative claim, because it just means are they linked together? Like, as one goes up, do I see the other one going up? But it doesn't necessarily mean there's a causal relationship. I don't necessarily know where the direct cause is happening, if it's this one causing that one or that one causing this one, or is there a third thing that influences both of them? So as we'll talk about in chapter 2, we'll talk about confounders, and we'll talk about this idea of identifying causal links and how tricky it really is. So, but for now, just realize that when we use a word like link or association or relationship or words like that, they're just talking about association, like just moving together, and that we would really want a word like effect or cause or things like that if we're looking for a causal relationship. So this is probably just an associative relationship. All right, so we'll stop there.